Today we're just putting together a very simple and quick model and let the BESO algorithm choose which elements it wants to remove from this structure. I've got the point load in the middle there and two supports, and I want to see what the BESO deletes. It's going to delete the stuff out of the end which isn't taking any load. If I keep going, it keeps deleting more and more. And if I make this into a cantilever, so I move the load over to the end point, you can see the tension and compression there in the orange and blue. And I'm going to let the BESO algorithm decide which elements it wants to delete to get what it thinks is a pretty efficient structure. Okay, so we're going to start off with a triangular grid, and I should say that this tutorial doesn't show off all the possibilities of the BESO algorithm, but it's just one quick method to get something running so that you can play around with it. There's plenty of other things you can do with it. So I want it in the XZ plane as the plane input. And I'm just going to set up some panels here. The grid size is 1. And the extents are going to be 100 and 10. So 100 long grid and 10 high. And sorry, that should be XZ. Already made a mistake. Good start. So this is an 100 meter long because Karamba uses meters. 100 long by 10 meter high structure of some type. I'm assuming it's a sort of bridge type structure. Now the next thing I want to do is explode the curves. And I want to get rid of identical lines because these are all polylines and you'll have some repeats for each segment. So in Karamba there is a component that does that. Remove duplicate. It's called RD lines. Now to do that, because they're in groups of 10, I'm actually going to flatten that. So we've gone in at 3,000 lines and we're coming out at 1,500 and a bit. Now I want to make this look faded in the background so I can see the actual structure that the algorithm has chosen. So I'm going to use display, preview, sorry, and a swatch. I'm going to make this sort of a grey colour. And I'm going to turn off some of this stuff so I can see what I'm looking at. So it's sort of faded in grey there, you can see. Make it a bit darker maybe for now. Okay, the next thing is I want to, similarly to the getting rid of duplicate lines, I'm going to get rid of duplicate points. And again, I'm going to flatten that to make sure. So we've gone in with 4,000, we've come out with 561. Okay, so the next thing we're going to do is get the Z component, because I want to find a support point on this grid. Just going to unpreview that. So get these points, turn them into their XYZ. and I'm going to use larger than. Larger than 0 for Z, and I'm going to cull a pattern. So almost all of these are going to be larger than 0Z. So it's going to cull almost all of them, but it should keep the top of the bottom row. Now I have to invert it. So now I've got a list of points, which is the bottom row of that lattice. And then from that, I want to choose my support points. So I'm just going to select an item from that list, set up a slider, and I'm going to go, how many items have we got? Got 51. So I'll get up to 50 because 0 is counted. Oops, and I want a real number, not a fraction. So now you'll see in green in the Rhino screen, as I move the slider, I'm selecting a support point. And I also want a load point. So just quickly, I'm going to sort these Z values. I'm going to reverse the list, grab the first item. So that tells me that the top of my structure is at a Z value of 8.66 roughly. And then I'm going to use larger than. So I want to check that whatever of these points has a Z larger than or equal to the topmost row. And then I'm going to use this cull again, cull pattern. So it's given me a true false pattern. And I'm going to use the actual points. And I'll have to use equals to, yeah, that's better. Because it's not larger than that number, it's equal to or larger than that number. Okay, so now I'm just going to copy and paste this so I can select from this new list a support point and a load point. This will be a point where I can apply my load at the top. Going to hide some of this stuff. So now onto the Canva part, and I'll do this quickly. Support. So position, we've got one position there already. I want Y, which is in and out of the page. Z, which is up and down, in other words, gravity. And I'm going to leave this one unrestrained in the X direction so that it can move. It's basically a roller. I'm going to copy and paste that. So that's my support point at this selected area, selected point, but I'm going to set one up at 0, 0, 0. So just a point. I'll manage that point collection. 0, whoops. Oh yeah, there we go, 0, 0, 0. And this one I will restrain in X, so that's support, triangular support, and that's a roller. So that's our supports, and we've got a load position. I'm going to add a load. If I go to the Karamba, load, gravity, I want a point. The position is that, we know that already. the force is in the Z direction, so I'm going to set up a unit Z, and I'll control the value of the Z vector. I'm going to make it minus 100. Put that into force. So I've got our supports and our load. The other thing I need is a cross section. And to do that, I'm going to use this. I won't go into this again, but I know that there's certain certain section sizes that Karamba knows straight off. Okay, assembling that structure. Got my loads, got my cross sections, got my supports. Oh, and of course I need my beams. So I'm going to use this line to beam. And we've already got the lines just here. They come out as elements. Right, we've assembled our Karamba model. So now we can use the BISO beam. And that is in here, BISO for beams. Plug that model in. Takes a little while, you'll see. Now I want to control some of this stuff. One in particular is the target ratio. I'll talk about that in a minute, but at the moment I'm just going to set it to 0.5. I think that's actually the default. The BISO factor is another one you can play around with. I'll just leave that as default now. Actually, I'll set up a slider so that we can control it later. Now I hope it doesn't, yeah, this needs to be a number. Well, actually I don't think it needs to be, but I'm going to make it a number. An integer. Okay, next, to see our results, I'm going to select a model, because it's given me a maximum displacement to the model, and it gives you a series of models. And you want to select one of those. So to do that, there's two ways of doing it. You can just select tree branch, but if you notice, this is a maintain component, so I'm not using that anymore. I'm actually using split tree, which I think is a bit more flexible, but it takes a little bit more to set up. But the number I'm going to select, I'm going to go up to 20, and I'm going to concatenate. And I just need to set up this to make a format that split tree uses, which is the curly brackets at the start and curly brackets at the end and the number in the middle. So that gives me curly bracket 0 curly bracket. That's my mask. And then for the history, which is a complete list of all the steps that the algorithm's going through. And by the way, I'm just going to simplify that. Now I do have a problem here, and that will be because I've got, that's it, that's the problem. See how I've got the one's a list of 0 and one's a list of 0, 0? I've got to flatten that. It's made two models for me, a list of lists. So I only want one model, that's better. So now if I simplify that history, I've got 0 to 30, correct. And I can just choose whichever one I want in the P, it'll come out as P, whichever history of that model, of that iteration. And I do that by using a Karamba component, which is activate. So I take the model and I put in the one that is active, and I can control that with that slider. So that gives me an active model, and I can put that into model view. So I'll just show you where it is up here. It's that one there, model view. So I've already got some results. I'll just go back to the start. I'll explain that in a minute. In fact, all right, I'll talk about it now. Actually, no. I'll put the beam view in as well, which is a further look at the. You can get the deflections out. So if I plug that in there, and I open up some of this, I want. That'll show me my results. I'll use that in a minute, but I'll just show you the display scales and the reactions, etc. So deformation up to 100, reactions 1. Loads, actually reactions down low. Now there's one thing I haven't put in there, which is analyze. So I want to actually analyze this model so I can see the deformed shape and I can see the reactions there. So the load scale, and the rest I can leave. So you can see how it's deformed. So if I move the load position right to the end, I'll just call this load position. Whoops. You can see that that's like a cantilever now, so it's deflecting at the end. If I put it in the middle, it's bending where the load's applied. Okay, so now that I've set that up, you can see the BESO algorithm in action. And at the moment, it's done no, I've selected the model that has no BESO applied to it. So now as I start to slide this up, you'll see it will try and get rid of elements that it thinks are not needed for this structure. So all this stuff at the end is not doing anything. The load is going from this point to these two supports. So why do we need any structure over here? Which makes sense. And at this point, it's got rid of all this useless stuff over here, and it's choosing to delete some of the inner stuff as well that it thinks it has minimal amount of load going through it. And it reaches a point where it maxes out, and that max point is controlled here as well at 10. So yeah, just as I hit 10, it stops deleting things and it starts moving things around a bit to try and refine it. Obviously you can change that, so you could keep deleting and deleting. And another way of controlling it is if I change this mass ratio. So at the moment it's trying to take 50% of this structure away. If I move that down a bit more, it's got a structure where it's trying to remove about 65%, say. Again, it removes all the useless stuff that it thinks, gets to about 10, and then it tries to refine that structure to make it perform a bit better. And you can see the forces. If I feel that, scale this down a lot, you can see the orange is tension, blue is compression, and that makes sense when you think about it. All those elements at the top are being compressed, and the bottom ones has got tension. So as I move that load, and the algorithms, I'll go back to 0, and then I'll move the load to the end, make it a cantilever. You can see you got a lot of tension over that support and some compression there, which makes sense. Now it's interesting to see what BISO wants to do here. What does it want to delete? You can see that it's deleting some stuff over here, which is useless. It's deleting a bit around here as well, so it's sort of doing an arch around here, and the tension's going in this top chord. And the bottom chord it's trying to keep generally because that's under compression, especially it's starting to get rid of. And you can see, ooh, so taking 65% of this stuff away is giving me a pretty funny looking structure. I'm going to make it half. Take out 50% of the structure. So deflection, if I look at the deflection of the original structure versus a maximum that the algorithm thinks you could get away with, it's not a lot of deflection difference, which is interesting. So I suppose that's the point of the algorithm really, is get rid of all the useless structure and just be left with the good stuff. Now I'm not saying that this structure is going to work either as well at the same time, because these are all just little CHSs, but obviously some of this stuff isn't going to work in compression. That's going to buckle straight away. There is a good way of limiting that, and that is if it's got a weighting of 1 for compression, I can reduce that to a half or even less. Even less would make more sense. So that just tells it you can't have a hugely long CHS sticking out in the middle of nowhere that's going to take a lot of compression, because that's not going to happen. It's going to buckle. So that does control it a little bit. However, I still don't trust that, because you would need to brace these up. It's thinking of these little elements as single entities, which they were modeled as, but actually that as one long line like that isn't going to work. So if you think about it, you could join those lines up and run this model again, and that will give you a better real life example, real life case. So it's not a perfect solution to all structures. You've still got to think about it in a fair bit of detail. But that's a basic BISO model running. But as I said before, this is just a very quick, simple model to get it running. From here you can play with all these values. You could run this as a 3D model. You could have it set out as columns and get the algorithm to delete the columns that aren't needed, for example, or there's all sorts of other things you could do. There's also another algorithm which I might do a tutorial for later, and that's the shell view version, and I would use that more for small scale stuff, so a custom beam or a wall element or something like that, where you want to remove material and get it as efficient as possible. So anyway, I hope you found that useful, but this is just the start. Thanks for watching this structured parametrics video. Leave a like or subscribe if you found this useful, and we'll see you in the next one.